So you can just understand this is there is a shaft, there is a wheel, and one side of the vane is shown here, side view of the blade of Pelton wheel. This is the jet which will be hitting the blades. Now if you look exactly this way from the bottom or exactly from the top, how it looks is something like this. The vane has got two parts. There is a splitter or a ridge. The incoming z, which will be having a velocity v1, the vane itself is moving with u, so relative velocity becomes v1 minus u, that is entering in, and then it gets deflected through an angle phi. Generally what we show here is a phi. This angle is known as phi dashed. So phi, the outlet angle, will be equal to 180 minus phi dashed. So obviously this jet is tangential, that's why it's called tangential flow turbine also. Now the typical inlet and outlet velocity triangles are this we have been seeing, our eyes are accustomed to this now. Only the change that has to be incorporated is something like this. This inlet velocity triangle will have alpha 0, theta 0. In the sense this gets flattened up like that. You can see alpha is reduced, theta is reduced, it is slipping down. Ultimately when it gets this way, that is exactly in one line, so it will be all the three vectors, that is z velocity, vane velocity, relative velocity, z velocity, vane velocity, relative velocity, all this become in one line. So to say, the v1 will be simply sum of u1 and vr1. So you can just see here, v1 will be equal to u plus vr, right? Vr. Now if you remember, component of z velocity in the direction of u is known as velocity of whirl. So here vw1 will be full value of v1, and then vf, that is velocity of flow, will be 0. Velocity flow is perpendicular to v1, vw1, so that is 0 here. That is what has to be appreciated here. So here inlet velocity triangle becomes just a straight line with v1 equal to u plus vr1, or vr1 equal to v1 minus u. vw1 will be equal to full value of v1, vf1 is 0. Now outlet velocity triangle, this z which is going out has got an angle of phi. vr2 is equal to vr1 equal to v1 minus u. So here it is, the relative velocity v1 minus u, it goes out, this angle is phi. So this jet relative velocity vr2 is shown over here, vr2 at an angle of phi. Now any u is velocity of vane, vr2 plus u should become v2. So this is the jet, angle of the jet is beta. So this is again a typical outlet velocity triangle, and these relations are quite evident from the figure itself, because v2 is there, the component in u is called vw2, the component this way will be called as velocity of flow. Now force exerted by the jet on series of vanes is given by rho av1, mass rate of flow, into change in velocity in the direction of x, that is horizontal. So here it is vw1 plus or minus vw2. So rho av1 in the bracket, vw1 is simply v1 from this v1 plus, because this angle is this way. Now vw2 is vr2 cos phi minus u. Now rho a v1 is vr1 plus u, vr1 plus u. VR2 cos phi minus u cancels off, so we'll be left with VR1 plus VR2 cos phi, but VR1 and VR2 are same as V1 minus u, so if I take common V1 minus u, I'll be left with 1 plus cos phi. So force exerted becomes rho a V1 into V1 minus u into bracket 1 plus cos phi. So force exerted is that much. Now work done becomes force into distance. Work done per unit time becomes force into distance divided by time. That is what is velocity. So this whole expression is as it is, into u is there extra. Now kinetic energy of inlet is half mv squared. M is rho a v1, that's why it becomes rho a v1 cube by 2. So hydraulic efficiency is work done by the jet divided by jet energy. If we simplify, we get an expression efficiency equal to 2u into bracket v1 minus u 1 plus cos phi divided by v1 squared. This is impulse turbine or Pelton turbine efficiency.